So today we're talking about momentum and impulse. Um, so we kind of discussed this in a previous workshop, but momentum, we're just going to go over this like pretty quickly, I guess. Momentum is basically defined as a state of a massive object in motion. So basically, if an object has mass and it's in motion, this object has momentum, and this type of momentum can be transferred to other objects during a collision. So it is the dot product of a mass and the velocity of the object. So basically the symbol of momentum is P, and then the formula is just P equals mv. Basically, if you guys know from earlier on when we discussed work and energy, the formula for kinetic energy is 1/2 of mv squared. So you can do a little bit of algebraic manipulation and find that K is actually P squared over 2m. This, although you don't have to know this, this formula does make it a bit quicker to calculate stuff, when you're trying to calculate anything, trying to relate momentum and energy. And the biggest law, the main law that you have to remember when dealing with momentum is conservation of momentum. This means that in any type of collision of two objects, unless there's an extra force involved, if momentum must be conserved. Basically, a momentum, since velocity is a vector property, it is a vector property. That means that the momentum has a magnitude and a direction. So we would write momentum can be expressed in this way, where P is a vector and it is going in some direction. So this, the net P before a collision and the net P after a collision must remain constant, unless, of course, there's an external force applied during the collision. So basically, if you have two objects colliding, which is most collisions, if you name these two objects 1 and 2, P initial for object 1 plus P initial for object 2 has to be equal to PF1 and PF2, where F just means final. Before Newton expressed his famous second law of motion with this famous formula, F equals ma, he did express it with momentum, where he did actually state that there was a proportional relationship between force and basically the derivative of the momentum, which is basically acceleration. But yeah, so this was his original writing. Basically, this was the original formula he stated in his, I think it was his Principia, if I remember correctly, but that was the first formula, the first way of expressing the second law of motion, because the derivative of P, or the derivative of mv, is ma, so it's still the same formula. Okay, well, most questions will not ask you to use derivatives. We're trying to find this, and basically at this level that we're talking about in this presentation is around AP Physics 1 and a little bit to AP Physics C, but not really there. So that's a bit unneeded. Impulse is basically what happens when the momentum changes, and it is defined as a force applied for a certain time. The unit for impulse is Newton seconds. So if, for example, you kick a rock, this rock had zero momentum before it, and the duration of the collision, let's say, is 0.1 seconds, and your force was 500 newtons. That means that you have instilled 50 Newton seconds to this rock, and it now has a momentum of 50 Newton meters per second. So this formula is J, the symbol for impulse. This should not be confused with the unit for energy, which is a joule, which is also capital J. Whenever you see J as a variable, it most likely reflects this in the problem because you never use a unit to denote variables. Basically, this is just part of the definition of what impulse is. It's the change or delta of P momentum, and it is basically what causes the object to change. So if you see like a force versus time graph like here, this area under the curve is your impulse. So if you guys know calculus, another way of writing impulse if the force applied is not constant during the time is that J is the integral of F with respect to dt. But you don't really have to know that for physics 1, really only physics C. And I'm pretty sure most of our problems will not be dealing with that. Basically, since the change in momentum is impulse, if an object has momentum before an explosion and it gets impulse, it's obviously the final momentum is just the sum of the two. And this was like the 3 types of collisions. You have elastic, where both momentum and kinetic energy is completely conserved. And for one-dimensional elastic collision, it's the sums of the velocities actually become the same if you derive that from the conservation of kinetic energy and the conservation of momentum formulas. Here you have a perfectly inelastic collision, and that's where basically the maximum amount of kinetic energy is lost, and that occurs when the objects literally move like they join together and start moving as one body after the collision. This does not have like a set like percentage of kinetic energy that has been lost, and it's often your job in the problem to figure out how much has been lost. Okay, so today we're going to do a lot of problems involving momentum. So let's look at question 1. So a baseball that has a mass of 150 grams is thrown with a speed of 20 meters per second. It is hit straight back towards the pitcher at a speed of 40 meters per second. This graph here shows the force time graph. So what is the maximum force that the bat exerts on the ball, and what is the average force of the bat on the ball? Since I cannot see the chat, if you guys have an answer, just unmute yourself and say it. So yeah, the chat's unavailable to me at the time, and I'll give you guys a couple of minutes to try to solve each part of this question. Okay, so does anyone have an answer? Should I just take this solution? You guys can say what to do next. So remember when I said that momentum has different directions? Here you must account for that by saying that these two momentums, the momentum before and after the collision, must have different signs. So it doesn't matter which one you give to which, you should get like the same magnitudes for the momentum, and you must know that the actual difference must be change in momentum. So therefore, this is your total impulse. So we know what the total impulse is, and we have a force time graph. So we have to use the fact that the impulse is the area under that curve, which if you saw was that graph on the other slide, it looks like that. This is the triangle. So basically the area of this triangle is the total impulse delivered. So this, we know the height is F max, and we were given the duration of this force, which was, it was 0.003 seconds or 10 milliseconds. So we can substitute that in with this formula. And then we can substitute in J with 9 kilogram meters per second. And we can solve for F max, which gives us 6,000 newtons. And then F average, remember the formula that the impulse is F average times T. We already know what F average is. We just found that out. We know, no, we don't know what this is. We know what T is, and we know what J is because they were already found in the problem. So F average equals to J over delta T, which is 9 over 0.003 or 3,000 newtons. So does anyone have any questions regarding this? If not, I guess I'll go on. If you do have an issue or a question, you're always free to unmute yourself and ask me. So we'll do this problem together. So we have a 12,000 kilogram railroad car that's traveling at 2 meters per second when it collides with another 10,000 gram railroad car that is not moving. If the cars end up joining or locking together during this collision, what is the final speed of the two railroad cars? So you have basically, this is what it looks like. This is before the collision. You have two cars on the rails, and then this one is 12 times 10 to the power 3. That's a pretty bad 3. 10 to the power 3 kilograms, and this one is 10 to the power 4 kilograms. And after the collision, since these two join together, that's effectively a 22,000 kilogram object that's just moving in one direction. So we're given this speed. This is 2 meters per second. And so we know that the momentum before this is completely accounted for by this 12,000 kilogram cart moving. So the momentum would be mass times velocity. So you'll get 12,000 times 2. So PI is 24,000. Yes, the answer is 12 over 11 meters per second. So basically, the P initial would be 24,000 kilogram meters per second. And so P final must be also 24,000 kilogram meters per second. So therefore, since the mass is 22,000, you would just divide by that and you'll get 24 over 22, which is the same thing as 12 over 11. So yes, you're correct. Here it's expressed in decimals because usually in physics you express things with like with a small number of significant digits. So, but again, this is kind of informal. This is not really a physics class per se, so I'm not going to require that in an answer. So here, this, even though it's a object that's moving on a string and it's bound by the string, it's still the same concept. So the mass of the block of wood is 2.5 kilograms, and the mass of the bullet that's basically hitting this block of wood is 0.01 kilograms. This block swings to a maximum height of 0.65 meters above the initial position, and your job is to find the initial speed of the bullet. So, why won't this click? You would still use the fact that momentum is conserved. So you start with this m1 v1 plus m2 v2 equals m1 plus m2 times vf. Why is it that formula? This is because the collision itself is just defined to be inelastic. Imagine there's a bullet that hits something, the bullet would become lodged in it, and while this is moving. So by definition, and by intuition, this should be in a perfectly inelastic collision. Manipulating term gives this color is pretty bad. Manipulating that equation to put it in terms to basically solve for V1, what you're trying to look for, the speed of the bullet, gives you this. So basically, it's the sum of the two masses, which we know each of these two masses times Vf. So what still applies here is conservation of energy. You have not applied any external force or work that to this motion. This thing is just moving by itself, and we are neglecting air resistance since it's just not said in the problem. So you would use the conservation of mechanical energy. So basically, when this was moving, it was at its maximum speed right after this collision. And when it reaches its maximum height, it stops moving. So basically, all of that kinetic energy becomes potential energy. So potential energy is mgh, kinetic energy is 1/2 of mv squared. So you equate these with each other. And then here, when we were talking about this energy and potential energy, since the block and the wood are together at this point, this m is the total mass, not the mass of the block or the bullet. So m1 plus m2 times gh is 1/2 of m1 plus m2 times vf squared. This is because this vf is still from after the collision. The two masses, these cancel out, so you have gh equals 1/2 of vf squared. Then you can move the 1/2 over, take the square root. Vf is the square root of 2 times gh, so this becomes 3.569. And that's basically the motion of the block and the bullet after the collision when it's joined together. So basically, now we have every single term we need in this equation. So just substitute in the values, and you get that bullet. You get that the bullet was traveling at a velocity of 896 meters per second before it hit the bullet. Sorry, hit the block. Okay. Next question. This is a very common question that this type of question is very common in physics, in like basic physics exams. And it's basically, you have two objects and one has a slightly larger mass than the other. So here it's m and 2m. They're often variables. So they end up undergoing a perfectly inelastic collision and start moving together. So does anyone want to tell me what direction these two objects going to go after this collision ends, and why? Does anyone want to tell me that? Yeah, so you can simply do this by comparing the momentum of the two objects. So basically, the momentum of this object would be 2mv, the momentum of this object would be mv. So let's define right as positive, as the positive direction. The momentum of this object becomes mv, and the momentum of this object becomes negative 2mv because it's moving left. So the initial momentum of these two objects together is mv minus 2mv. So the momentum is negative mv, since right is positive, this is moving left. So we have mv plus 2mv equals 3m times, and this becomes, so basically we have that this total thing is negative mv, and we know that the combined mass after the collision is 3m, so you can simply plug in and solve for what the final is, and then you can just compare the total amount of mechanical energy before and after the collision. Since here there is no potential energy, the objects are not above the ground, and there's no elastic potential energy because they're not like being compressed by a spring. This here mechanical energy is basically just K. It's just kinetic energy. So let me show you. So basically, Vf, since the net momentum is negative 3m, is negative mv, and the total mass is 3m. Vf equals 0.3 in the negative direction. So to find the total amount of mechanical energy before, you would just sum up the kinetic energies of the two objects that are moving. So 1/2 mv squared plus 1/2 of 2 mv squared. And then you subtract the final result, which is 1/2 times 3m times v over 3 squared. Combine, just make the denominator the same. Do arithmetic on the numerators, simplify the fraction, and you'll get that the total amount lost is 4/3 of mv squared. So that answer was C. Okay. This type of question is a conceptual question. So let's say we have a stationary object and it bursts apart. So it breaks into 3 objects. So basically, let's say we have this object, and each of these are one of the shards of the object after it breaks. One of them goes up here. So basically, one goes here, one goes here. That's not the scale. These two move at the same speed, and they have the same mass. So these two left and right objects both have a mass of m, and they both travel at the speed v, and then they're asking for what is this. It's not in that direction, but what's basically, what is this velocity here? We know the mass here is 3m. So how you do this is that the main defining concept here is just conservation of momentum. This object was stationary before the explosion, which means that no velocity and therefore no momentum. So this means that since there's no impulse here, this means that these vectors have to add to 0, because the vectors beforehand, before the object exploded, there was no vector, it's 0. So that means that the vectors afterwards must be so the vectors at the end basically must add to 0. So so basically this p vector must basically have must have components of -1. If you define this as the origin, this as positive x and this as positive y, to make things easier, this must have a magnitude of -1, -1. So you have that it's not 1 here, sorry. Negative mv, negative mv, sorry. So basically 3mvf is basically that. It becomes that. It becomes a magnitude of that. So we can get rid of this, and we basically have vf is v over 3. And then that's just one component of that though, so you have to multiply the square of 2 to get the actual magnitude of the vector itself. So the answer should be D. You could have probably done this by process of elimination by first noticing that, of course, due to conservation of momentum, that this would start moving in the direction that's down from left. That just immediately gets rid of A and C. And you will also notice that B does not take into account that the masses are different. B is what would happen if the 3 pieces had the same mass. So you could also have done this by process of elimination. So yeah, the answer is D. This is basically what momentum is basically good for, like in real life, and that's basically when you're playing pool and you're trying to figure out how to get the ball so that it falls into the hole. This needs geometry because and physics. So basically, if you know, you would know from momentum that if a ball strikes a wall and there's no impulse or anything added, it would it would fly off and get at the exact same angle measure. And if there's no energy transfer, basically, if the ball's not losing energy by friction, like if you're playing ice hockey, if you're playing like the air hockey, it should move in pretty much the same velocity as well. So this is a bit useful, I would say. So here we have the ball with mass m traveling with a velocity v, and it strikes a wall at an angle of theta if, with respect to a line perpendicular to it. So just look, you can look at this diagram for reference. It rebounds with the same speed and same angle. This normally happens if there's no external force, like if there's no like spin or friction or anything like that. This basically is asking you what is the impulse delivered by the ball to this wall. So how you would do this is that you must look at this in terms of x and y separately. So it's just like kinematics in the fact that you should analyze it by each component. So that's what it looks like, this angle of theta. So the angle is the same, v is the same, and basically, therefore, if this is y, there's no change in the momentum in terms of this up-down direction or the direction the wall runs. So the main difference here is that it travels in the opposite direction. So that's accounted for by the x component. So it starts moving right, but then the x component starts moving left, and this must have been from the impulse. So delta p is j, and that's delta p is just mvf minus mvi in terms of the x direction. We were not given the direction of the component itself, so we must find that out using basically vx equals v cosine theta. So you have mv cosine theta minus negative mv cosine theta, if you find this as positive. So you get basically it's 2 mv cosine theta because these two add up, and this is your total change in momentum. And the impulse that's delivered by this to the wall must be the same as the impulse delivered by the wall to the ball. That I'm pretty sure that's because of Newton's third law, which is basically every single force has an equal and opposite reactionary force. And so, yeah. So this is a bit more complicated. I guess I'll read the problem and highlight the important parts of it. So you have a rope of L, and let's say there's like an imaginary suspension or something at this point C. A person is here at where this point A is, and he's gonna basically swing into the ocean. So like that kind of motion. And then he sits at a ledge here at position A, and basically when he sits here, this rope is stretched completely. So it's completely tightened, and because the rope has this exact length L. The person then drops off this ledge, swings, which is basically in a quarter circle formation, and it basically he hits and grabs this object M2. Let's say it's like a bag or something, and then this person and M2 and this object of M2, they would start falling towards the lake, hit here at D, and basically, we're going to ignore air resistance and rope mass because let's just assume the rope is really light and it just complicates things further. We also know that D is a vertical position L, that's the length of the rope, directly below B. So here, these three parts require you to derive an expression for each of these. So what is the velocity? Not just speed, I guess here, but velocity. Speed is the magnitude of velocity. Just before colliding with this object, what is the tension in the rope just before the object collides? And what is the total horizontal displacement x of the person? Basically, what is this length here? From A to D, what's the horizontal distance? Each of the expressions should be expressed in terms of only four variables, M1, M2, L, and G, and any fundamental constants. I'm pretty bad at moving back towards the slides, so if you guys want to try to note down this diagram, you can. Okay. All right, so we're going to go to the solution. So the first one, as you could probably tell from what kind of problem this is, a person's falling from a height and they're asking you to speed at the bottom. This is a conservation of energy problem. So here is when the person is initially above at point A and just lets go of the top, like starts falling. That is all potential energy. And then let's say that position B is H0. So wherever this point is, where M2 is, let's find this as a height of 0 for now. Since the rope is out and the person doesn't just crash onto the floor, we actually know that this height is L. So that's kind of like, this is kind of like what a poorly drawn diagram of what's happening. So the potential energy at A has to be the same as the kinetic energy at B because energy is conserved. So you would basically say that mgB, mgh, so here's L, equals to 1/2 of mv squared. Here, this M does not reference the M2. I guess this is pretty obvious enough. Here, M references the person. Just wanted to clear that up. Okay, so the M's cancel. GL is 1/2 of mv squared. So 2GL equals v squared. And so the velocity is square root of 2GL. Okay. Part B needs you to analyze this point. So this one requires you to know about how rotational dynamics works, since this is actually the person is undergoing a circular motion. So at this point, the main forces are these two forces. So you basically have a tension that's basically the rope stretching to keep the person to try to kind of lift the person up, because the rope itself is stretching and it does not like the stretch. And you also have the force of gravity that's doing the work of pulling the person down. And this is a circle, so there's definitely centripetal force involved. And the formula, if you guys forgot, for centripetal force is mv squared over r. And this actually should account for F net, since other than these two forces, there's no other forces at hand. And so these two forces must account for centripetal force. Centripetal force by itself is not a force. It's not a defined force. It relies on other defined forces to like kind of like constitute it. It's constituted by other forces. So you can just say that Ft minus mg, which is F net, equals mv squared. V squared is 2gl, and then over L, because here R is L. Cancel the L's. So Ft minus mg equals 2mg. Move the mg over, so you get Ft equals 3mg. Question 3 asks for the horizontal distance, and this needs kinematics. So they're asking you for what is this distance, and in order to find that, you have to actually find what the vertical distance from here is. What's the vertical distance? What's the horizontal distance? Sorry, from here to here, and then you can just tack on an L, since this distance is L. This is the same as the length of the rope up here. So the only thing that's constant here, since this is general motion, the only thing that you should really rely on is time, or t. So we should first analyze the y direction before, in order to calculate t, and then just apply t to find the x direction. So the formula for distance is v initial t plus 1/2 of at squared, and here the only real a in the y direction is g. So you have your v y initial, and here when it's at this point, the person and the object is just heading straight right. There is no up down velocity, so we can just straight up put that as 0. So L is just gt squared over 2, and rearranging to put t in terms of L and g makes this thing become t equal to the square root of 2L over g. So this is just 2L over g, and then you have to use the formula of Vx equals dx times basically dx equals Vx times t. So this is notated wrong, but you could just move t over, and we already know what t is. So dx equals Vx times square root of 2L over g, and then you could basically just do this. X equals to v constant, just square root of 2L over g, and then remember to add on that L because you have to count for this distance as well. So yeah. Are there any questions regarding this? Or are you guys completely okay with this? Do you guys just understand all of this? No? Okay. Well, the foundations are basically just rooted in math. So yeah, just practice these types of questions, and you'll eventually just get used to doing this kinds of stuff. You don't need a particular strong affinity for physics in order to do this kind of stuff. Okay. Okay, so question 8 is having 2 balls on a frictional horizontal tabletop, basically a plane. This is a 2-dimensional. In 2 dimensions, it's still the same law. It's still conservation of momentum. Here, it's just that it has to, unless like the things collide like in a weird way, such that there's extra force applied, the momentum vector should be the exact same before and after. That means that, yeah, the speed has the not only like the magnitude of momentum, like you would normally find in a 1D momentum problem, but also the direction must be the same, and any answer choice that doesn't, that ends up like having the momentum changes direction just by a normal collision, it would be still wrong, just like 1D. Here we have an elastic collision with two identical balls, and one is moving at 10 meters per second, and the other one's initially at rest. After the collision, ball X moves at 6 meters along a path at 53 degrees to its original direction. So let's say, so here you have a ball X that's moving here, it hits Y, so hits here, and then this moves. So can anyone tell me what direction should Y move? I'm trying to get to the chat box, but I'm having a hard time doing so. So if anyone has an answer, just please say it out loud. It would make my life easier. Oh, it's okay. I accidentally showed the answer. Okay, since I accidentally showed it, okay. Since I accidentally showed it, I guess we'll just go over it now. So basically, Y should go 53 degrees down. Why is this the case? It's because the momentum in the beginning is all accounted for by X, and X is moving straight right. So it means that even though there's a direction change in X, the direction change in Y must be the exact same relative to the horizontal axis. So since this is 53 degrees, this must also be 53 degrees. So you can look here, and you can just immediately just knock out A, B, and C. Like you can knock out all of these. All you have to know is that like this direction is the same. A doesn't work because Y would have to move. Y has to move because ball X ends up slowing down anyways after the collision. That means that some of the momentum must have been transferred to Y and therefore must be moving. B and C have the wrong direction. It should be 53 degrees down. It should not be 37. The reason they put 37 there is to trick people up into thinking that, oh, well, it moves down and right, and this forms a right angle, so it must be intuitively okay. This only works if this is a 45-degree angle, like just perfectly diagonal. In this case, it's not. And yeah. So diagram D is the best answer. We already know why this is 53 degrees. And for the 8 meters per second, you would just simply just analyze this with respect to the X component. So the Y components here have to be the same. This 6 cosine 53 has to be the same as this. And then this has to be the same. Has to be, so this extra X vector has to be 10 minus this 6. So you can use a calculator for this for in your spare time, just like change the numbers a little. But yeah, you would get 8 as your final answer because it's just 10 minus 6 times the cosine of 53, and then you have your two components for the Y vector, and just square those and add them up. One should be a cosine and one should be a sine, just square together, and then you should get pretty close to 8. Okay, so next. This is gonna be, I think, our final question. So here you have a force time graph again. The object has mass m. So even though this is quite irrelevant, they are asking you what is the total change in momentum, or what is the total impulse of the object from this graph from 0 to 4 seconds. So this is basically, you're trying to find the area of these two rectangles. So how this would work is, remember, no, it's not A. The answer is C, actually. I said earlier on that here it's the area under the curve. It's not exactly that. It's like, by definition, the integral of force with respect to dt. An integral does account for the fact that there is a negative area. So basically, when you're doing the area summations for 0 to 2, this area here is just 10 times 2 equals 20. But here, since this goes down to -2, you actually have to say that this is 10 times -2. So this becomes 10 times, or here, -10 times 2, and then this becomes -20. So you would add these two numbers up, and your total impulse would be 0. So I guess you can think about it as, let's say an object. Here it doesn't start at 0. It starts with some acceleration, basically 10 over m. But for simplistic purposes, for like conceptual purposes, let's say it starts from rest, and suddenly a force of 10 newtons is applied to it. So you think about this object going faster and faster, forward and forward, and then this occurs for 2 seconds. When we say negative force, that means that the force is now starting to be applied in an opposite direction, and it's still 10 newtons, and basically, and it's still 2 seconds. So the total impulse that's counteracting this change in momentum, this change in momentum back, has to be equal. So P starts off as 0, it increases, it hits its maximum here, and since this occurs, this force is in the opposite direction, P begins decreasing, and then by the time P equals 4, it's 0 again. So does everyone understand that? Okay. Yeah, so the area of the FT graph is the impulse, which determines the momentum change. The net impulse in this case is 0. So there will be 0 total momentum change. So the answer was C. It turns out we have one more question. So a bullet of mass m and velocity v0 is fired towards a 4m mass block, and the block is initially at rest on a frictionless horizontal surface. So that means that there is no friction that is counteracting the moment. There's no friction that can act as impulse to like slow down the momentum. That means that the momentum is completely conserved. The bullet penetrates a block and then emerges. So it goes in and then goes back out. And it emerges with a velocity of v0 over 3. Okay, and then there's a few parts here, and it's to determine the final speed, the loss in kinetic energy, and the gain in kinetic energy of the block. And then you have to obviously, since they don't give you numbers, you're supposed to express these as algebraic expressions in terms of v0 and m, because those are your two variables. So I'll draw the diagram if it confuses any of you, but here you're still going to apply conservation of momentum. So you have that bullet, and this bullet was traveling at v0, and then this was 4m. This was 4m. Then it ends with this block traveling with some speed right, and then the bullet is traveling at a speed of v0/3. Okay. So we know that momentum is conserved. So that means that the change in momentum in v0, this change, must have been the change in momentum for the block. So here you can set up your equations such as like this. P initial is P final. So mv0 is mv0/3, and then plus 4m times vf. And then you'll move this here, so you get 2/3 of mv0. I'll abbreviate this a lot. So this is equal to 4m vf. And then just cancel the m's, divide by 4, and then vf is v/6. So that's part A. They're asking what's the final speed. It's moving right, and the speed is the exact same as the velocity. So it's v0/6. The next was the total loss in kinetic energy. This is referencing the bullet, since this block gained kinetic energy, and this is an elastic collision, so it should be overall the same. So you have KEF minus KEI, and then you just put in the formulas. 1/2 of mv² is kinetic energy, so you would have, this is 1/2 of mv0², because it's traveling at v0 beforehand. It was traveling at v0/3 afterwards, so they just subtract, and you get it's 4/9 of mv0². And then it's not elastic. It never said it's elastic, so you actually have to independently find what's the kinetic energy of the block. So KE is 1/2 of 4m times v0/6². It's the exact same formula. You just use your answer for part A and the mass of the block. So this becomes 1/8 of mv0². So the main thing to watch out for B and C is to not assume that just because the collision is one-dimensional and both things start moving, just because both of these things are moving afterwards, does not make this an elastic collision. Elastic collision specially dictates that the kinetic energy has to be the same. Here it is a partially inelastic collision. This is because energy is lost, actually. You can see from here, you have lost 4/9 of mv0² of kinetic energy for this, and only gained 1/8 mv0² of kinetic energy. So this system in total has actually lost energy. But it's only partially inelastic because, again, these objects are not fully bound together. So it's not a perfectly inelastic collision. Okay. So that is the end of all the problems. It's a bit overtime. It's 7:05. If you guys have any questions, I'll be happy to stay here and answer them. And if not, I wish you all a happy weekend. And I guess I'll see you later in another physics workshop. Okay. So, yeah.